welcome back to Fat Mama Physics. In this video, we're going to continue with examples on Faraday's law. And in this question, we're actually asked to predict the direction of the current. So you definitely need to know what Lenz's law is. Of course, for both laws, it's better to fully understand how it works, which this video is not going to cover. Okay, so starting with example 3. Let's do this in green. Maybe let's do it in blue pen this time. Okay, a circular coil of wire, radius 2.5 centimeters. Okay, let's draw a diagram here. So we got this circle, terrible drawing, but alas. Okay, so I'm actually gonna draw this actually like a circle, not from like a side view or anything. Okay, so here we have this radius. This radius is going to be 2.5, or that's just 0.025 meters for our radius, okay? It is placed in a magnetic field, and this is, this time we are told the direction of the magnetic field. So the magnetic field is going into the page. I'm just going to write 1x here, just so we don't have, I think there's going to be other things we need to draw later on. So I'm going to write here the initial field is going to be into the page as 0.020 Tesla. The field is then reduced to 0.01 Tesla into the page. So the final field, here I'm just going to write that for directionality because the field has direction. It still is into the page, but it is reduced to 0.01 Tesla. It does so in 0.10 seconds, so that's just going to be our change in time. What is the average induced EMF? And it looks like a single wire, so it's not, the end value is also going to be 1 here, okay? So we're going to apply Faraday's law, so that is just the EMF is equal to, and I'm just not going to write in the negative because the negative is only for the direction of current. We'll do that in D, okay? So this is going to give me N delta phi over delta T. So number of loops is 1. Actually, well, here, let's just write it out. And if the only thing here that is changing is the field, the area of this loop is not changing. It's not getting swept over or anything. And so we'll just look at the change in field. The change in field is going to be from, we're just going to designate into the page as positive. So the final is 0.01 Tesla minus 0.02 Tesla. The area is going to be, well, it's a circle, so that's still pi r squared, in which the r value is 0.025 meters squared. So putting that in, that's going to be pi 0.025. I can't fit that unit in there, so here we go. Divided by the time, which is 0.1 of a second, okay? So putting that all into our calculator, the change is actually just 0.01. I get 1.963 times 10 to the power negative 4 volts. So that is, how many sig figs? 2 sig figs. That means the 6 is going to round the 9 up. This is going to give us a 2.0 times 10 to the power of negative 4 volts. Okay, so there it is. Let's figure out the direction of the current. All right, so guess what? The right-hand rule here is going to look really funny on screen. So I hope you will be doing this along with me while I give you instructions. So I will insert another page. Hopefully this next page will be able to help you out. So let's have a loop of wire. Okay, the magnetic field is going into the page. Okay. And then what's going to happen is that the magnetic field will be reduced, which means we're going to have a change in magnetic flux. So if we use our right-hand rule, and mine is going to look weird on screen, you just have to listen to my instructions, okay? So put your pen down. Don't use your left hand. That's the first thing you have to be careful. Use your right hand. Your thumb, we're going to use our thumb as a direction of the magnetic field, and we're going to use our fingers for the direction of the current around the loop of wire. So imagine you're going thumbs up, and then the direction of your curl of your fingers are going to be the direction of the current. So the magnetic field is into the page, and it will be reduced going into the page. So we have to oppose that change to predict the direction of the current. So what does that mean? It means that this current that will be produced in the wire has to make the current in which the magnetic field that it creates is going to counter this change. So whatever opposes this change. So when the magnetic field is reduced, in a certain direction, the opposite of that is to supplement more magnetic field, or to supplement the magnetic field in that direction. So the current that's produced is going to create a magnetic field going into the page because it counters the change of it being reduced. It counters the reduction. It is to, so that's what we're going to do with our thumbs. So if you have the page right in front of you, you're going to take your thumb and you're going to stick it into the page. Pretend you're sticking into the page. And that's going to show you, watch your fingers curl around that, and it will show you that your fingers are going to curl in the clockwise direction. On screen is going to be a mirror, so I'm not going to attempt that. So if you put your thumb in, I wish I could draw this, but I'm just going to butcher it. So if you put stick your thumb into the page, you'll watch your fingers curl clockwise, okay, around the loop. So that is how you deduce the fact that the magnetic field, the current, the induced EMF will produce a current through this wire that is clockwise, okay? So we also get clockwise. All right, okay, so that was A versus B. I actually want to do a quick pivot. Not a quick pivot, but actually a tag-along question. Because in this question, notice that the field is reduced to something into the page. What happens if the magnetic field is now out of the page? So I'm going to go to a quick example. Hopefully it won't be too bad. So the magnetic field, we're going to go from 0.02, was it? 0.020 Tesla. It's going to start off into the page. So I have the X for that. And it's going to be changed to 0.010 Tesla, so same magnitude, but this time the magnetic field is going to go out of the page, okay? So again, same thing. We're going to try to calculate the induced EMF, and we're going to try to predict the direction of the current. So let's see what we can do here. We know that the EMF induced is the number of coils times the change in magnetic flux over time. The rate of change, which includes time already. The coil is one coil, okay? We have one coil, and we do have a change in magnetic field times the area divided by the time which is provided is 0.01 seconds. So with one coil, which will go away, the change in magnetic field, and this is where you have to put in the directions. You have to think about the directions. I am choosing into the page as positive. So if it's going out of the page, which is a final here, the final going out of the page, that's going to be negative for me, 0.010 Tesla. And I'm going to subtract the initial, which is this one, and this one is into the page. So that's going to stay positive. So I'm just going to write that here. Going into the page, this is going to be positive. It looks like multiplying plus. But that's going to be our positive direction. Let's just write direction here, okay? All right, so that's going to subtract 0.02 Tesla. That's going into the page. The area, which is pi r squared, and I believe r was 0.025 meters squared for the radius, divided by the time 0.01 seconds, or did I get that? No, 0.1 seconds. And the radius is correct. So 1 less 0, okay? And here we go. So notice that the overall change in the magnetic flux is going to be a lot greater because you're going from one direction, you're switching directions essentially. So effectively, you're adding the two numbers, 0.01 plus 0.02, that's going to be 0.03. Remember, we're not going to really care about directions for now because we will do that when we consider the direction of the current, which comes later. Okay, so here I get 5.89 times 10 to the power negative 4 volts. And if we round to 2 sig figs, that's 5.9 times 10 to the power negative 4 volts. Okay, so notice that is a lot bigger than our previous one. Now let's try to determine the direction of the current that would be produced. So we got this coil. The magnetic flux is going into the page, but now it's coming out of the page. Okay, so think about Lenz's law. We want to oppose the change in the magnetic field. So imagine this current, okay? Again, you put your pen down, right hand out. So we have the the magnetic field increasing going out of the page. So again, we're not gonna like that. If it's increasing going out of the page, then the field lines, the induced current, will have to produce a magnetic field that goes into the page. Again, eh? So as you go into the page, because the flux is increasing out of the page, so going into the page counteracts increase going out of the page. So again, the thumb goes into the page and it also curls in the clockwise direction. So in this case, it would be clockwise again. So then you're thinking, well, how is that exactly the same as the previous case? Well, true that. First of all, in the previous example, it was a reduction going into the page. So you have to supplement. You have to oppose the reduction by adding more to a magnetic field in that direction. In this one, the change is going out of the page. Increasing going out of the page means you have to supplement one going into the page to counteract the increase going in the opposite direction. Okay, so think about, maybe the challenge for you is to think about in what scenarios would you get a counterclockwise current, okay? So we're going to end the video there. I'll probably talk a lot with an extra example there. So I hope you learned something from this video that you can apply to your practice. Wish you good luck, and Fan Mama Physics signing out.